what I'm going to start with, basically going back to some of the rules for drawing the Lewis structures, because that's essential to know when you're dealing with drawing the three-dimensional shapes. And then we'll go through some of those rules, and then we'll get into how to use those to actually create a three-dimensional structure for these molecules, because that's really the essential part of the whole chapter, is understanding the three-dimensional shape, because the three-dimensional shape determines a lot of different things. Determines polarity, which we'll see is extremely important, and it also determines reactivity. Certain shapes are a lot more reactive than others, and so we'll see why that is, looking to see how the electrons are organized around the outside of these molecules. And then we'll look into learning. We've already learned about slightly about ionic bonding and covalent bonding. We'll learn that there isn't a sharp transition between this bond as ionic and this bond as covalent. We'll learn that there's something called ionic character, that certain things you would assume to be an ionic compound aren't really, based on the difference in electronegativity. And I posted a couple of different tables in Canvas for you to either print out and have nearby, or have on a screen you could look at, because we'll be referring to the differences in electronegativities a lot, and we'll also be referring to the different molecular geometries and molecular shapes. And you don't have to memorize all that, because that's kind of ridiculous. You have to memorize all these strange shapes and weird words to describe them. But what you will need to learn is, based on the Lewis structure you created, what general group of geometry is that, and then based on where the bonds and the lone pairs are, what molecular shape that is. And that is all in tables that I posted for you to look at. So I would recommend you either print those or have those open on a window somewhere. Okay, so let us press on. So I've been talking endlessly about the octet rule, and that, when we draw a Lewis structure, the first thing we need to do after figuring out how many electrons there's going to be is we fill out octets for everybody, starting with the peripheral atoms, the ones on the outside. Fill them all up with electrons. You give them lone pairs until they get an octet, and then if there's any electrons left over, you put those in the middle. Well, that's not always going to be the case, because there are certain elements that are electron deficient. They don't have enough room, they don't have enough space, they don't have enough electrons to take on a full octet. The obvious one is hydrogen. It's only got one electron. It's not going to add another 7 electrons and take on a huge negative charge just to get an octet. It can't do that, because it only has the first shell with room for 2 electrons. That's it. Boron and beryllium are also electron deficient. Beryllium is element number 4. So it only can make 2 bonds. That's it. It can't make any more. Boron can only make 3 bonds. It can't make any more. So those 2 are electron deficient. They will not form an octet. So be aware of that when you're making those structures. And then something else I sort of talked about a little bit. When you're adding up the number of electrons that are going to be in a molecule, almost always it's going to be an even number. Why? Well, because electrons hang out in pairs in their orbitals, right? I mean, we have bonds or pairs of electrons, double bond or 2 pairs of electrons, lone pairs, pair of electrons. So generally, the total number of electrons in a molecule is going to be an even number, but that's not always the case. Sometimes there's going to be an odd number. And when you have an odd number, that means that one of the atoms is going to have basically a single electron or an odd number of electrons. And we call that a radical or a free radical. We call it a free radical because basically these things run free, trying to pair up that electron as much as they possibly can. I think I mentioned one of the examples that you have in your house right now is hydrogen peroxide. So that's the structure of hydrogen peroxide. And right now it is not a free radical because it's all paired up. But what happens when you pour it out onto like a cut or something like that, this bond breaks. And when it breaks, because those two oxygens pull on electrons exactly with the same strength, what happens is that one of them will pull one electron away, the other will pull the other electron away, and what you wind up with is this. They each have an odd number of electrons. It's not charged because it's got 6 valence electrons, but it is extremely reactive because this single electron here is unstable. It needs to get paired. It needs to form a bond, or it needs to steal an electron away from somebody else. And that's why hydrogen peroxide is so destructive to basically the biological molecules in particular. Because biological molecules are like long strands with lots of electrons in them. And so hydrogen peroxide, or this peroxide ion, which isn't really an ion, will come along and pull off an electron. And so it's a radical, it's very reactive, and it is really good at killing things. The other exception to the octet rule that we've mentioned a lot is when you get into past the second period into the third period. Now the third period means, on the periodic table, means we now have 3 subshells, right? It means we have 3s, 3p, and 3d. With 2, we only had 2s and 2p, 2s2, 2p6. There was only 2 plus 6, 8 places to put electrons. That was the total number of spaces they could put electrons. When we add another shell, now we have 3s2, 3p6, 3d10. We got a lot of places to put electrons now.
Excuse me.
Yes.
No, is that possible it's available for those many electrons, but is it stable though?
Well, think of the total number of valence electrons. Total number of any largest number of valence electrons any atom can have is 8, right? So you could have a total of 18 electrons in there, but it's doubtful. I don't think anything actually makes that many bonds. Okay. Because the only things that could would be noble gases. And once you start taking electrons away from noble gases, they become much, much more electronegative. And so they start pulling back on those electrons. But as we can see here with sulfur and phosphorus, they violate the octet rule routinely. Sulfur has 6 valence electrons, just like oxygen. So you can see here the sulfate ion, sulfur in the middle is forming 6 bonds. And so it has a total of 12 electrons, but it only has 6 valence electrons. Now remember, the valence electrons are lone pairs that an atom keeps for itself, mine, and 1 electron from each of the bonds. And so it's got 6 valence electrons here, which it should have. And so there's no charge, no harm, no foul. Then sulfur does this all the time. And same with phosphorus. Phosphorus is in group 5, just below nitrogen. So it can form 5 bonds. It has 5 valence electrons. So in this situation, it has a total of 10 electrons from the 5 bonds, but it only has 5 valence electrons, 1 from each bond. And so that's cool too. Again, no harm, no foul. And so when you're drawing these structures, when you see a structure that has either phosphate or sulfate, or I keep saying phosphate and sulfate, either phosphorus or sulfur in it, know that there's a very good chance that the octet rule is going to be violated, because that's something that phosphate and sulfate do all the time. In fact, probably more often than not, because a lot of the times they're bonded to things like oxygen, which is very electronegative, takes electrons from it, and so it forms lots and lots of bonds to get to the total number of valence electrons that it needs. Okay, so I think we've hopefully we've all seen this before. But yeah, sulfur and phosphorus are the 2 classic ones that violate this rule, possibly more than anybody else. So let's just do a couple of examples. Let's do the first 2. What would be the name of this compound right here?
Xenon tetrafluoride.
Bingo. Very good. How is that possible? That how could, I mean, xenon is a noble gas. How can it can form a compound? I thought noble gases didn't do that. What is it about fluorine that you can form this compound?
Is too electronegative.
Yeah, it's because fluorine's so damn electronegative. Fluorine can take electrons from pretty much anybody, with the exception of like helium and neon. I don't think any fluoride compounds have been detected, but or argon. I don't think argon, but krypton and xenon, fluorine has been able to make compounds with, because it's so electronegative. It doesn't matter who it's coming up against. It can take electrons from it because it's so strong in pulling electrons away. So who would be the central atom in this particular molecule?
Xenon.
Yeah, it's going to be xenon, because it's not going to be fluorine, because fluorine can only form 1 bond. So there's no point putting fluorine in the middle. So there's a lot of things going on. Generally, if there's just 1 atom in the molecule, it's usually going in the middle. And remember, if it has a lower electronegativity than fluorine, and everything has a lower electronegativity than fluorine, it's going in the middle. So we're going to put xenon in the middle. So there's our xenon, and we'll surround it with 1, 2, 3, 4 fluorines with 1 bond each. All right, so let's count up how many electrons there are going to be. How many valence electrons does xenon have? Valence electrons in xenon. What group is it in? 8, that's right. It's in the last group. It's the noble gas group. It's group 8. It has 8. The only exception to that being helium. And which group is fluorine in? It's a halogen. It has 7. That's right, Jessica. Excellent. And there's 4 of them, so 4 times 7 is 28. Now, is this a charged molecule? Do we need to add or subtract any valence electrons?
No.
No, there's no charge here. So 0. It's a molecule. Remember, anytime it says molecule, that means no charge. So 28 times 8, that's 36 electrons, if I'm not mistaken. How many electrons do we have in bonds? How many electrons are in bonds? We got 4 of them already there. So how many electrons have been taken up already? Ferrous, right, 8. We've taken up 8 because remember, each of these is 2 electrons. And this is really helpful. I've mentioned this a bunch of times, but it's super helpful to put those electrons there. Just as a reminder, A, it tells you how many electrons are in a bond, which is always a nice thing to remember. And the second thing, it really helps in determining formal charge when we're figuring out how many, the difference between total electrons that go into the octet and valence electrons, which determine the charge. Because when we determine the charge, we basically split these bonds down the middle and give 1 electron to one atom and 1 electron to the other atom. So we have 8 in bonds. That leaves us with 28. So we have 28 electrons. And remember, what I like to do, what you should do, is decorate the exterior of your molecule with electrons. All the atoms on the outside should get a full octet, unless they're hydrogen. And remember, they only get 2. So let's put 6 more electrons on each fluorine. So 1, 2, 3, 4, 5, 6 gives that fluorine a total of 8. 1, 2, 3, 4, 5, 6. That gets 8. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's 24, leaving us with 4 left over. So where do the 4 left over go?
Around xenon.
The middle.
Goes in the middle. Yeah, anytime you have electrons left over, you put them in the middle. So we'll put 1 pair there and 1 pair there. Now, let's figure out if there's any charges that we need to deal with. So how many valence electrons? Now we're not dealing with total this time. How many valence electrons does each fluorine have? Now remember, 7. Right, where do you get the 7 from? Where do you get that number from? I mean, it should have 7. Where do you get, how does it have 7 here? I only see 6 valence electrons. Where's the other one?
The other one is from the bond with xenon, half of it.
That's right, exactly, perfect. Yeah, for formal charge, we figure that they're sharing those electrons equally. They're playing nice and they're sharing equally. So that would be 2, 4, 6, and then that 1 for 7. So each of the fluorines has 7 valence electrons. It should have 7 valence electrons, so none of them are charged. And the more of these you'll do, you'll see that there's a pattern that reappears over and over and over again. Anytime you see a halogen with a single bond and 3 lone pairs, it's not charged because that's 7 valence electrons. Anytime you see an oxygen with 2 lone pairs and 2 bonds, that's not charged because it has 4 in the lone pairs and 2 in the bonds for a total of 6. It's not charged either. That's 6 valence electrons like it should have. And same with nitrogen. Nitrogen will have 2 lone pairs and 3 bonds. That's 5 valence electrons, which it should have. And so it isn't charged either. So basically, the more of these you do, these patterns will keep showing up and you'll be able to just look at it and go, okay, that's not charged. I can tell already. I don't even need to add it up. But it's a good idea to add them up now until your brain is programmed, until I brainwashed you into being able to do this properly. All right, so what about xenon though? Let's look at xenon. How many valence electrons does it have? How many should it have, first of all? Now, remember what group xenon was in and how many valence electrons it should have.
8.
Should have 8. So how many does it actually have? I can see 4. How many does it actually have here?
8.
Where do they come from?
4 bonds and 4 that
So there's
I mean,
4
two
from the
lone pairs.
bonds and 2 lone pairs for a total of 8. So it's not charged either. So this would be, man, it's an ugly structure we got here. So what we're left with is something that looks like this. So we have xenon in the middle with 2 lone pairs and 4 bonds for a total of 8 valence electrons. And that's fine. It can have 8 valence electrons and a total of 2, 4, 6, 8, 10, 12 electrons because it has an expanded shell. It has a d orbital. It can put electrons in. So that's not a problem. And then all the fluorines have their 7 valence electrons and a total of 8. They have a full octet. So in this instance, everybody's happy. Okay, let's look at a little more complicated one. This is phosphoric acid. So what we're going to do is the hydrogens are connected directly to the oxygens. So we don't need to worry about that. So basically we're going to do PO4 and then put like phosphate ion and then put the hydrogens on the oxygens, okay? So with PO4, who goes in the middle?
So the hydrogens are on the oxygens.
Yes.
So oxygen in the middle.
Why would oxygen go in the middle?
Wait. Hydrogen goes to
We're just going to draw PO4 right now.
phosphorus.
Phosphorus goes in the middle. Why is that?
It is least electronegative.
Yes, there's 3 reasons it
less-
goes in the middle. First of all, there's just one of them. That's the first reason. Second of all, yes, it's less electronegative than oxygen. That's reason number 2. And 3, it can form more bonds than oxygen can. That's basically the 3 really good reasons for putting phosphate in the middle. So let's do that. So put phosphate in the middle, and then 1, 2, 3, 4 oxygens around it, and we'll give each of them a bond. Okay, so how many total electrons should we have? How many valence electrons do we get to play with here? Phosphate has how many? Phosphorus, I keep doing that. Phosphorus has how many valence electrons? What group is it in?
5.
5. It's in group 5. It's right below nitrogen. So notice that if it's just below nitrogen, chemically it should react a lot like nitrogen. It usually has 3 bonds and a lone pair. Here we see it's slightly different. So it has 5 valence electrons. And oxygen, you should all know by now, has how many?
6.
6. And phosphate has a charge of what? Do anyone remember what the charge on a phosphate ion is?
-3.
Yes, -3. So we have 5 plus 4 times 6, which is 24, 29, plus 3, 32 electrons. So as I mentioned, go round the outside for filling up octets. So we go 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So that is 6 times 4, that's 24. We have 8 electrons left over. What did we forget to do? We forgot to do something. We have 8 electrons left over. What did we forget to do?
Hydrogen?
Not yet. We're going to do that next.
Put in the phosphorus.
Nope, not yet. We forgot to do something.
Ah,
Where do those? Where are those 8 electrons? They're already on.
the bonds.
They're in the bonds, right? We have 8 electrons in the bonds. So 1, 2, 3, 4, 5, 6, 7, 8. So they're already there. So basically, that's all the electrons we have. There's none left over. So the oxygens all have a total of 8 electrons. Their octet is full. Now, if I look at phosphorus, it has a full octet as well because it has 4 bonds with 2 electrons each. So it has a full octet. So as far as the total number of electrons they all have, that's fine. But let's look at the formal charges. Now, what would be the formal, since all the oxygens are the same, they should all have the same formal charge. How many, let's calculate what it is. So how many valence electrons should oxygen have?
6.
Should have 6. And how many do they actually have in
7.
this particular picture?
7.
Where did the 7 come from?
6 plus the 1.
6 plus the 1. I need a little more information. Where's the 6 and where's the 1?
3 lone pairs and 1 in the bond.
Right. So we have 2, 4, 6, 7. So each of them is negatively charged. So we have a negative, a negative, a negative, and a negative. So we have 4 negative charges. What about the phosphorus? What is the total number of valence electrons phosphorus is supposed to have?
5.
It's supposed to have 5. And how many does it actually have here?
4.
So its charge is +1. So one thing I want to point out here. When we're drawing phosphate ion, one of the things we've sort of told over and over again when we're drawing these sorts of structures, we want to reduce the total number of charges as much as possible. So the total number of formal charges, we want to reduce the number of formal charges as much as possible. So in this instance, everybody has a charge. So that's as many formal charges you can possibly get. But look and see, we're supposed to have a -3 charge. And if we add them all up, we have -4 plus 1. So that's the right number of charges. But it's argued that you would want to reduce the total number of charges as much as possible. So what would happen, and this has been taught for years in chemistry classes, is we would take one of these lone pairs from one of the oxygens and make a double bond. And what that would do is give phosphorus 5 valence electrons and eliminate the charge, and give that oxygen 6 valence electrons and eliminate that charge, leaving only 3 oxygens with negative charges. And then each one of those would then bond a hydrogen. And so when you're drawing H3PO4, that's a fine way to draw it. With one of the double, so with H3PO4, with here, there's no charges. There's no charges at all because this becomes bonded, this becomes bonded. And so each of the oxygens has 2 bonds and 2 lone pairs. And that's fine. And the phosphorus has 5 valence electrons and 5 bonds, so it's fine. But what I want to point out is that one of the things I've been mentioning over and over is that nature loves symmetry. And what's been found just in the last couple of years by scientists trying to figure out what the structure of a phosphate ion actually is that This is the actual structure of phosphate ion. If you calculate these bond distances between the phosphate and the oxygen, they pretty much match up to what you would expect if there was a negative charge here and a positive charge here. So for phosphate ion, this is an acceptable way to represent it. You can also represent it with a double pair, with a double bond, and no charge on the phosphate and no charge on that oxygen. That is also acceptable. Either one is acceptable. Just know that one of the things I constantly try and hammer home is that anytime you can draw a symmetrical diagram, most likely that is going to be the one that you'll actually find in nature, whether or not it violates some sort of rule against formal charges or anything else, because symmetry basically trumps almost anything else.
Is it more like resonance?
Right. Yeah. So the old way it was taught, it was that it's a resonant structure, but it's been found since then that the ion itself is not really a resonant structure. It is a permanent symmetrical molecule, but either one is acceptable. Okay. Does anyone have any questions about that? No, I sort of spent a lot of time on that, but I sort of just basically want to bring you up on what the latest chemistry is. And so let me show you the way that you'll see it taught. You'll see it taught like this. This is what you'll see when you go to your textbook and you read about it. You will see that this is the structure I showed you, where phosphorus has a +1 and each oxygen is negatively charged when it doesn't have the hydrogen on it. Now it says structure 1 obeys the octet rule, but has formal charges in it. And so it says that is not as stable as this structure, which doesn't have any formal charges. And that may be true for the acid form, where there's no charges, but with the ionic form, where there are charges, structure 1 is actually more stable than structure 2. So this isn't something you need to worry a whole lot about, because either one is legitimate. But just know that when you're drawing these things, if you can come up with a structure that is completely symmetrical, that is probably going to be the proper structure that actually occurs in nature. Anyone have any questions about that? So there's a difference between looking at the ion and looking at the molecule. They're going to have different structures. So structure 2 for the molecule is probably more stable because there are fewer formal charges. But that's not necessarily true for the ion. Okay?
Mm.
All right. It's enough babbling. So I'm going to skip this one and then keep going because I want to get to polarity. That's basically what we're really getting down to. So hopefully everyone has either seen the I posted a table with electronegativity in it. There's also a number of slides here. There's a whole bunch of slides in the deck here that have electronegativity table in there. Really, there's only a couple you should come to mind, like fluorine is really, really high, and then like fluorine, nitrogen, oxygen, carbon. Look, those are like the basic 4 that really are helpful to know. So a covalent bond is basically a shared pair of electrons, right? But they're not always shared equally because one atom will have a greater ability to pull on that electron cloud And remember, I've sort of been trying to make the point that it's important not to think of this pair of electrons between these two carbons as like two dots in space, because they're not, as we've seen with last chapter and good old quantum mechanics. It's a cloud of distribution, and that these two electrons basically spend their time moving back and forth in this cloud between the two electrons, between the two carbons. So when each of these two carbons has the exact same electronegativity, so we would expect this to look fairly symmetrical, that the distribution would look pretty much the same all the way across. And so they have an equal, those electrons have an equal chance of being close to one carbon or close to the other, the same. However, you put carbon next to fluorine, same pair of electrons, same electron cloud. But now that electron cloud is much more close to fluorine and just a little close to carbon. Because fluorine is so electronegative, it pulls on that cloud. Its nucleus is pulling on that cloud of electrons more than carbon can. And so this cloud gets pushed slightly closer to the fluorine. And so that becomes polar. And we call this a dipole. Polar means there's basically two poles. One that's slightly more negative, and we use this delta to indicate slightly more. So the fluorine is slightly more negative because it has slightly more electrons in its vicinity than the carbon, which becomes slightly positive. And we call that a dipole because it's got two poles, one slightly positive, one slightly negative. And we represent it in a couple of different ways. This is one with the delta, delta minus, delta plus. Delta plus goes to the atom that has lower electronegativity. The delta minus, which has a little more electron density close to it, gets the delta minus because it's it's not a full charge. It's not like it steals out the pair of electrons completely and takes them all the way away from carbon. But like the more popular stepdad, it keeps those electrons a little more close to it and a little further away from the carbon. So it's slightly negative, not completely, okay? And so this is the different kinds of bonds we get based on that. As I mentioned at the beginning of the class today, we're going to find out that there's not really there's a completely ionic bond, there's a completely covalent bond, and then there's a gradation in the middle where we see where we can say bonds have more of an ionic character. Oops, let me go back. So pure ionic means there's absolutely no sharing of electrons at all. So basically it means that this atom has completely given up any access to that cloud of electrons. That cloud of electrons that you form in a covalent bond is completely left. And so since it's completely left, this becomes positively charged. And this larger electron cloud has gone completely to the non-metal or the negatively charged. And so it now has a completely negative, it's a full negative charge. It's stolen that pair of electrons entirely. And so the positive ion has no access to it at all. But we see that as the difference in electronegativity between them gets smaller and smaller and smaller, they start to share a little bit more. And look at the size of the negative ion and the size of the positive one. The positive one starts to get a little bit bigger, and the negative one starts to get a little bit smaller because now that electron density starts to move a little bit more to the positive ion. And now it's not completely positive anymore. it's a little positive, but it's not completely positive, because now the electron cloud isn't completely pulled away from it. It's getting a little bit of it, but not as much as if it was an atom unto itself. And then finally, we have a pure covalent situation here, where that pair of electrons is shared completely the same. And this will happen when you have like two hydrogens or two oxygens or two fluorines, or any diatomic molecule is going to be a purely covalent, because each of these atoms is identical. So they pull on that electron cloud exactly the same. And so it's going to be exactly the same around each of them. Each atom is going to be exactly the same size, because the electron cloud is exactly the same size. And that is a purely covalent bond, making a non-polar covalent bond and a non-polar molecule. There's no difference in electronegativity between those two. And so it is not polar at all. There's no poles. Nobody is partially positive. Nobody's partially negative. Since there's no poles, we say it's non-polar. Okay? And here's the breakdown. So this is where it really, really is essential to have that electronegativity, easy for me to say, that electronegativity chart in front of you. Because all of these, let me go back, all of these are based on the difference between them. So for instance, carbon, fluorine, where is it on the table? Well, carbon, I think, is around 2.5, and fluorine is 4. So the difference is around 1.5. And so we can see that the cutoff, so the general cutoff between polar and ionic is around 1.7. So it is just below being an ionic bond. So it is extremely polar. This is a very polar bond, because the difference is 1.5. That's a very, very polar bond. And pretty much anything fluorine is bound to, it's going to be a polar bond, except itself, of course. Now, the higher and higher we go, the more and more ionic it gets. So up at the top is here where we see like metals and non-metals, like sodium and fluorine, like sodium fluoride is extremely ionic, because sodium has a very low electronegativity and fluorine's the highest. That's about as ionic as it gets. And then you start getting the differences down here, where the difference is around 0.4, 0.5. That starts going from being polar to being not so polar, like carbon, hydrogen. That difference is around 0.4. So we say that isn't very polar. That difference is not great enough to affect the pulling of the electron cloud one way or the other. So we say that's a non-polar bond. And then when the difference is 0, that's completely non-polar. So it's a gradient. Anywhere in between 1.7 and 0.4, we say it's polar. Anything less than around 0.4, we say it's non-polar. And then anything greater than 1.7, we say it's ionic. But really what we're saying is that bond gets more and more ionic character as we move, as the difference gets greater and greater. Okay, any questions about how these things break down?
I kind of have a question about this. I was just wondering which bonds are harder to break.
Ionic.
Okay.
Yeah, the ones that's the strongest bonds. We're going to show you in a second. That's an excellent question. I'll show you in a second. We can measure this directly by looking at the boiling points or the melting points. When you break the ionic bonds, when you melt them, and that's why ionic compounds don't melt until you get just extremely high temperatures. Now, when we melt polar or non-polar, we're not actually breaking the bonds, the chemical bonds between them, but we're separating the molecules. And so that's not nearly, it doesn't take nearly as much energy to break those. So, but you can get a general idea of how strong the ionic bond is by looking at the melting point.
But
So-
why is it relatively easy to break it in water?
Oh, because you're not breaking the chemical bonds between the atoms when you have a covalent bond. When you boil water, you're not breaking the covalent bonds. But when you boil salt, you're breaking that ionic bond. So it takes much more energy to do that. But if you want to compare the strength of ionic bonds, you do that by looking at the melting point, because you actually are breaking the chemical bond there, because they're held together by that ionic bond. By turning it into a liquid, you have to break that for them to become mobile. But with water, you're not actually breaking the covalent bond when you boil it, right? You're just turning it into steam. It's still water.
I mean, when we dissolve it in water, it breaks, right?
Mm-hmm. Yes, an ionic. Yeah, you'll break it when you, some ionic bonds will break when you dissolve them in water. The less strong ones. That's another way of determining how strong an ionic bond is, whether or not it dissolves in water. Weaker ones will dissolve in water, and stronger ones will not. Yeah, anytime you pull the two ions apart, either by melting it or by dissolving it in water, you're breaking that bond. So the stronger ones do not dissolve in water, and the weaker ones do. That's
So
another way of looking at the strength.
I could assume that the
Okay.
ones that dissolve in water have a lower melting point.
Exactly right. That's exactly right. And I'll show you some examples. So let's look at. Clear that. Let's look and see what those bonds actually look like. So if this is just a diagram showing you where the electrons are relative to each atom. So if we basically plot where we're going to find the electrons in a bond between two hydrogens, we're going to find them pretty much equally around both nuclei, and then slightly less in between. But you can see it's completely symmetric. So we can, if we just made a line right down the middle, we can see that's completely symmetrical. So each atom basically has the same distribution of electrons. That's a nonpolar bond. Well, then when we look at F2, the bond in between, that's sharing an electron as well. But you see there's a lot more electrons because fluorine has 7 valence electrons, hydrogen only has 1. But again, if you put it right down the middle, you can see that they're equal. This distribution on this fluorine is exactly the same as the distribution on the other fluorine. That's a nonpolar bond. But put hydrogen next to fluorine, and you can see now it's unequal. So most of the distribution is completely around the fluorine, and if we draw a line between down there, you see it's not equal sharing. That shared pair of electrons spends a lot more time in the vicinity of the fluorine than it does to the hydrogen, and that's a polar bond. And this is the other way that we represent it, with this symbol here. That is a symbol for a dipole. Now what it does is that we point it toward the atom that has more electron density around it. In this instance, the fluorine. Those electrons are spending more time around fluorine, so we point towards the one that has basically the slightly negative charge. And we point away from the one that has a slightly positive charge. And if you forget which direction, notice that this has like a plus sign in it. And the plus sign points towards the slightly positive atom. So there's two things to know about this particular symbol. One is that it points towards the more negative atom. So wherever the electron distribution is higher. And the size of it is dependent on the difference in electronegativity. So if I have a slight difference in electronegativity, it will be smaller. If I have a much larger difference in electronegativity, it will be bigger. And so we need to pay attention to both the size and the orientation of the dipole. Now, these are bond dipoles. This is a bond dipole. This tells us whether this bond is polar. We'll learn that once we draw our diagram of the whole molecule, and we draw all dipoles for all the bonds, then we're going to basically add them together and see which direction they point in to determine whether or not the whole molecule is polar or not. Does everyone understand the difference? We're going to do some exercises to show the difference, but we're going to start with a bond dipole where it points to the more electronegative atom that has more electron density around it. Okay?
Professor,
Yes.
do we use dipoles in ionic bonds as well, or just in covalent to show where the higher region is?
You can use them in both, but in an ionic bond, that dipole would be huge because all ionic bonds are polar, all of them, and so automatically you're going to have a dipole. Not all covalent bonds are polar, and that's why we use them to show the orientation of the dipole and then how big it is. So for ionic bonds, you're going to make these huge dipoles. But yeah, they're present for ionic bonds for sure, but much bigger. So again, here's our electronegativity scale. You can see it goes up as we go across. And I just basically want to point out the period 3. So I'm going to show you compounds taken from period 3. So this is period 3 here, starting with sodium and ending with chlorine. And you can see as we go across, the electronegativity gets higher and higher and higher, starting with a very low sodium, even less than 1, and chlorine is 3. So as we go across and make different compounds with chlorine, that difference in electronegativity is going to start really, really big and then get smaller and smaller and smaller and smaller as we go across. And you'll see what effect that has on those compounds. All right, let's do that. So here's the first compound. Good old sodium chloride. So you can see that the difference in electronegativity for sodium chloride is like around 2.1. So that's ionic. And if you just even look at the sodium chloride, you can see there's all the classic, it looks like an ionic compound. You get crystals that look like an ionic compound. You remember all ionic compounds give you these sort of crystalline solids. And sodium chloride is a classic crystalline solid that melts at a high temperature and conducts electricity when it's melted. Okay, that's an ionic compound, no doubt about it. Let's move over one. Let's look at magnesium chloride. Now, magnesium is slightly more electronegative than sodium is because it's the size of its cloud is slightly smaller. And you can see the difference in electronegativity now is slightly smaller. It's now around 1.8. Still an ionic compound. And you can see that you've got crystals like you did with sodium chloride, and it melts at a relatively high temperature, still an ionic compound. And when you melt it, it conducts electricity. Okay, ionic compound. Watch though when you get to aluminum chloride. The difference between aluminum and chlorine is now around 1.5. So it is now moving into polar covalent territory. And look at the difference in the structure. Now, notice how it kind of looks like a powder now? You don't really get those big crystals like you did, like with sodium chloride, with table salt. You get those nice big crystals. You don't get those nice big crystals anymore. You sort of get this, what looks like a fine powder. And now it melts at a relatively low temperature. It melts at 200 degrees. And when you melt it, it barely conducts electricity. It conducts it a tiny bit, but not really that much. So this is what we would call a polar covalent bond with some ionic character. So it's close to being an ionic bond, but it's not quite. It's polar, it's very polar.
And excuse me.
It's not completely polar. It does have some ionic character because it does conduct electricity. Yes.
What is the conductivity measured based on? What's its unit?
Oh, conductance. It's actually, I think it's Siemens, millisiemens. Basically, it's like how many electrons can move per unit volume.
Okay.
Yeah. So basically, the more electrons can move, the more conductive it is. So the difference.
So it's not like electronegativity is not based on a thing.
Is not what?
Compared to a thing, it just never mind.
Yeah, just send me a note if you want to. Yeah. So what we're dealing with is these bonds are becoming less and less ionic and more covalent. But you can see that there's not the super sharp cutoff, because here we have something that's polar and yet slightly ionic. So we can say it's very polar, but it's also slightly ionic. And then when we move from aluminum to silicon, we can see that now the difference is around 1.2. And so now it has no ionic character at all. In fact, this is now a liquid. You can see that it's a liquid now. It's not a solid. At room temperature, it's a liquid, and it does not conduct electricity at all. And so its melting point is actually below zero. And then we keep going. We get phosphorus trichloride, and then we get to sulfur dichloride. And by the time we get to sulfur dichloride, that difference, it becomes very small. And then now it's almost non-polar. It's right on the edge of being non-polar. And so you can see, if you can tell, if you can like look really closely at the container it's in, you can see that there's some gas in there. So it is a red liquid. So you can see that it's a red liquid. You can also see some reddish gas inside as well. So what that tells you is that it has a high vapor point. It has high vapor pressure. It has a very low boiling point. And so that liquid is being turned to gas quite a lot at just room temperature. So that is barely hanging on to being polar. And by the time we bond chlorine with itself, that's completely nonpolar. There's no difference in electronegativity. And now we have a gas. So you can see that when there's very, very strong polarity, you get a solid. When the polarity becomes weaker, you get a liquid. And when you have no polarity at all, you get a gas. And that's when we talk about the way molecules interact with each other. This is something that will be important to discuss, is how molecules interact with each other is really based on how tight the interaction is between the atoms in the molecule itself, and whether or not it's polar, non-polar, or ionic. So any questions about this? Do you see how the molecules change as the bonds change and become more and less polar? and how we can tell the difference? I always love this slide. There's a lot going on in it. Why are there negative melting points? Oh, negative melting points just mean they're just below zero. Yeah, this just means they're liquid at room temperature. That's all. So, depicting polar bonds. As I showed you, there's two ways of doing it. One is by using the delta symbol. So we get the delta plus and delta minus. But when you're drawing a molecule, that's not as helpful. When you see like a single bond, it helps because it indicates which atom is more electronegative and where most of the electron density is going to be. But when you're drawing a whole molecule with lots of different atoms, I find this one is a lot more helpful because it shows you the directions. So you get the relative size, how long this arrow is, and the direction that it's pointing will help you determine whether or not all of those bonds add up to a polar molecule. So when you're drawing a molecule, I recommend using the arrows and not using the delta signs, okay? Because it will help a lot more. So let's do a quick exercise. So I'm going to use that arrow and indicate the polarity of each one of these bonds. So we've got a hydrogen-nitrogen bond, a fluorine-nitrogen bond, and an iodine-chlorine bond. So that's the first one. And then the second one, we'll rank these three different bonds with increasing polarity. So the first one will be the lowest polarity, and then to the highest. So to do that, we're going to need our table. So I just went ahead and put the table here. So starting with nitrogen, hydrogen. So we'll just draw it. Oops. Use a different color. Here we go. Here's a nice color. So I've got hydrogen, nitrogen. Which way should that arrow be pointing? Who has a higher electronegativity? Hannah, left. What does that mean?
Nitrogen.
Towards. Go ahead, Hannah, you can tell me.
Pointing towards nitrogen because it's bigger than hydrogen in electronegativity.
Bigger in electronegativity,
yeah.
yes. Right. So the arrow points towards nitrogen and we put the plus sign in there, indicating that the hydrogen is going to be slightly positive and the nitrogen is going to be slightly negative. That's right. So what about a fluoro-nitrogen bond? Which direction should that be pointing in?
Toward fluorine.
Fluorine.
Towards fluorine. And that's kind of an easy one. It always points towards fluorine because ain't nobody more electronegative than fluorine. So the only time it doesn't point towards fluorine is when you have fluorine gas. That's it. Every other time it's bound to anything, it's going to point towards fluorine. So that way. What about an iodine-chlorine bond? So here I've got my iodine, here I've got my chlorine, and that can form. Iodine is a big big atom, and so you can steal electrons from it. So which direction would the arrow point? Or would there be an arrow? So is it pointing toward the iodine, pointing towards the chlorine, or is it no arrow at all?
It's pointing towards the chlorine.
Pointing towards the chlorine. And would I make a big arrow or a small one?
It's about 0.5
Mhm.
difference, so I would say a relatively small one.
Right. Yeah, you make a relatively small arrow pointing towards the chlorine. So here's a question. Notice that there's no electronegativities given for the noble gases, but there actually is. In the table I gave you, there actually are electronegativities given for krypton and xenon. Why don't helium, neon, and argon have an electronegativity?
Because they are small.
Nope.
Mr. Noble Gases.
Well, yeah, but krypton and xenon have electronegativities. What's different about neon, helium, and argon? I mean, Raymond was right. They are smaller, but that doesn't explain why they don't have, like, it hints as to why they don't have an electronegativity.
The electrons are closer to those three atoms than the xenon and what?
Yes, you're getting close. That's another reason why they don't have it. It's not the reason, though. Nothing in the chat. What does electronegativity mean? Go back to what the meaning of electronegativity is. How do we measure electronegativity? Electronegativity is measured when there is something. What is that something?
So the bigger atoms, when electrons go to them, they do not. They are not very sensible.
Mm-mm. What do you actually have to have in order to measure electronegativity?
Electron.
But everybody's got electrons. What are you actually measuring? Electronegativity is the difference in electronegativity between two atoms in a, or two atoms that are something together.
Covalent bond.
That are bonded, right? If you don't form any bonds, you can't have any electronegativity. So helium and neon and argon don't form any compounds. And so you can't measure their electronegativity because they don't ever share electrons with anybody. So you can't form, if you can't form a compound, you can't measure the electronegativity. On the other hand, krypton and xenon can form compounds, with fluorine in particular. So you can measure the difference in electronegativity between fluorine and those two. Just a little something there. So let's see if we were right about those. Right, so points towards nitrogen, points towards fluorine, points towards chlorine. Excellent. And we sort of skipped over this part, but yeah, the most polar, oxygen has the highest electronegativity, nitrogen slightly less, carbon less than that. So the least polar bond would be hydrogen-carbon, followed by hydrogen-nitrogen, because the difference in electricity is greater, and then the greatest difference is between hydrogen and oxygen. Okay, so in the sort of 10 minutes we have left, I want to sort of start the introduction to the shapes. Oops, let me go back. Now, we're going to take basically all the stuff we've learned so far and move it into what the shapes are going to be. So the shapes are going to be based on something called VSEPR, or which is something called valence shell electron pair repulsion, which is a very fancy way of saying electrons are negatively charged and don't like being close to each other in space. That's all that means. So we're talking valence shell electron pair means pairs of electrons that are in bonds. So this is an electron pair. And this is an electron pair. And they don't like being close to each other in space because they're negatively charged. And so if you have a lone pair of electrons and a pair of electrons in a bond, they are not going to be attracted to each other because they're all negatively charged. Duh. So they're going to repel each other. And basically all we're going to see, all this VSEPR nonsense means, is that bonded pairs of electrons and lone pairs of electrons will arrange themselves in three-dimensional space to be as far away from each other as possible. That's it. So if you can think in 3 dimensions, I can't. I can barely read a map. But if you can think in 3 dimensions, this will make perfect sense to you. It's like, yeah, they're just trying to get away from each other as much as possible. They try and get maximum separation, because maximum separation means lowest energy. And everything in nature likes to go to the lowest energy state it can. And in this instance, in a molecule, the lowest energy is have the fewest repulsions, the fewest repulsive energy between electrons. So if they can get as far away from each other as possible, that lowers the repulsive energy between them, leads to a low energy molecule, leads to chillaxing, and that's all molecules want to chillax. So what does that mean? As I mentioned, you just get those valence electrons as far away as possible. That's all it means. The other thing to remember is that a group means any group of electrons in space. So if I'm looking at a single carbon-carbon bond, remember, that is just a distribution of electrons in space between, and the space is between those 2 carbons. If I have a carbon-carbon double bond, all that means is twice as many electrons in space between the carbons. That's where they are. That's where you will find those electrons, is between the 2 carbon atoms. But now twice as many. So that's also one group. It's one group with twice as many electrons in it. If I have a triple bond between those 2 carbons, that just means I have 3 times as many electrons in that space between the 2 carbons, because that's where they are. That is also one group of electrons, because it's in that space between the 2 carbons. It just means there's more of them. Now, every group is just a group of electrons in a particular area in space. That's all it means. So it can be a lone pair, it can be a single bond, a double bond, or a triple bond. It doesn't matter. It's just a group of electrons in space. That's all it means. So they all count as a single group. And that'll be important when we're figuring out what the shapes are. Okay, so those are like there's only 2 rules in figuring out the shapes. Know how many regions of electron density there are in space, and the regions of electron density is a bond or a lone pair. That's it. And then be able to tell the difference between a bond and a lone pair. Those are the only 2 things you need to remember. Everything else will be in these. You don't have to memorize these. These are in tables that I have sent you already. So just think about this. If I have 2 groups of electrons in space, where are they going to go to be as far apart from each other as they can? Well, 180 degrees apart. They can't get any more apart than that. If you bend them in one direction, or you bend them in the other direction, or forward or backward, they get a little closer together. So they're going to be, whoops, keep forgetting to do that. They're going to be in a line. That's the way they're going to align themselves. Bad pun. Yeah, so they will be, that gets them as far apart from each other as they can. in a line, 180 degrees apart. So that'll be a linear conformation. What if you have 3 groups of electrons around the central atom? So here's my central atom in the middle, and it's got 1, 2, 3 groups of electrons around it. Now remember, it could be lone pairs, could be atoms with a single bond, atoms with a double, atoms with a triple. They all mean a group of electrons in space. What shape will it take to get those things as far apart from each other as possible? Well, they'll stay in a plane, but this time instead of 180 degrees apart, they'll be 120 degrees apart. So 1, 2, 3, and separate it by 120 degrees. They'll look like that. Because if they go above the plane or below the plane, they get a little bit closer to one of the other groups. So if they stay in a plane, that gets them as far apart from each other as humanly possible. If they change that angle from 120 degrees, they get a little bit closer. So they keep it at 120 degrees. If there's 4 regions, then you start to get 3-dimensional shapes. You start to get like a tetrahedron, a tetrahedral shape like a tent. And this particular bond angle, these are all angles between the different atoms. So this is the angle between an atom on the outside, the atom in the middle, the central atom, and another atom on the outside. This number will come up over and over and over again. That is the angle when you have this tent or this tetrahedron. That's the angle between them, 109.5. That gives the maximum distance in 3-dimensional space from each other. And then when we get to 5, we get this weird shape where we have 2 positions on top and on bottom. We call those axials because they look like an axis through the Earth. And we call these 3 on the outside, 1, 2, 3, circumference. They're on the periphery. They're around the middle. So that's what we give them, basically the same name as we would. Equatorial. We call those the equatorial atoms. And so there's 2 different angles here. One, there's a 90-degree angle between the axial and the equatorial. So that's 90 degrees. And then there's that same 120-degree angle between all the 3 around the equator. Okay? And then finally, when there's 6 electron groups, we get what's called an octahedral shape, where everybody is 90 degrees apart from each other. That's the maximum distance you can get when there's so many different groups. So what we'll learn next is we'll take the number of atoms that are around each central atom and the number of lone pairs, and that will determine the actual shape of the molecule. These are the general shapes for the number of groups, but the actual shape of each molecule will be determined by how many of these groups are atoms and how many of these groups are lone pairs. And so we'll pick up with that next week. And we'll also learn how, by looking at the different dipoles associated with each of these groups, we can take the dipoles. This shows us how they're arranged in space. Either they're linear dipoles or they're in a plane pointing in 3 different directions. We put all those dipoles together and we can figure out whether or not the whole molecule is polar or not. Okay? So, questions so far about this? I know there's a lot to drop on you, but we're gonna pick this up on Tuesday and start putting it into practice. When we start putting it into practice, it'll start making a lot more sense. So Raymond's got to go. So any questions before we call it a day?
I have some questions regarding recitation 7.
Mm-hmm.
I'm not sure what to fill out for regions of electron density and
These are
polar or
regions of
non-polar.
electron density. So regions of electron density are a lone pair, a single bond, a double bond, or a triple bond. Each one of them counts as one. So that is a region of electron density. So it's these things that you're looking at right here. Those are regions of electron density. So with these balloons, so each one of these balloons, like for instance, let's look at the second one. So this could be a lone pair, or it could be an atom that's single bonded to the central atom, a single atom that's double bonded to the central atom. It could be that as well. And so that determines the overall shape, what group it's in, the overall geometry. And then the actual number of lone pairs versus bonded atoms determines the actual shape of the molecule. But each one is a region of electron density.
Wait, so is the number of bonding regions going to be the same?
Sorry?
Like, is it going to be the same for the number of bonding regions?
Oh, okay. Let me pull up. Let me pull up a whiteboard. Hopefully this will explain it a little bit better. So if I have, let's say I've got this molecule, formaldehyde. So this is formaldehyde. You may have heard of it. So there is my structure for formaldehyde. How many regions of electron density are there around the carbon?
3.
3, right. 1, 2, 3. Now, it doesn't matter for the overall geometry of the molecule how many electrons are in each one. We just want to determine what geometric group it fits in. So there's 1, 2, 3. So that tells us that it's trigonal planar. But the number of electrons in each group will help determine what the shape is. Because what we're going to learn is that because there's more electrons here, there's more electrons here than there are here or here. So what that does is actually this double bond will repel slightly these two groups of atoms away from the perfect 120 degrees. Should be, like if it was completely symmetrical, it'd be 120 degrees. We'll learn that that double bond actually pushes these two hydrogens together so that angle is now slightly less than 120 degrees. So it's important for the shape, but it doesn't matter for the overall geometry. It is still trigonal planar, but its shape will be slightly different based on what those different groups are. But the number of groups, lone pairs or bonds, doesn't matter. That tells us the geometry. What group are we in? The number of lone pairs and what kind of groups they are, double, single, double, triple bond, will influence the actual shape. But it will be still in the same group, but it'll determine like the bond angles and that sort of thing. That's what we're going to learn that next week.
Wait, so what would we put for bonding regions on the recitation?
Bonding regions, 3.
So it's the same as the regions of electron density.
Yes. Well, no. What we'll learn is, we've sort of gone over this with the other two groups, so you're little bit behind. So we're going to learn this rule, like the Axe body spray rule, that will help us determine what shape the molecules are in. So A stands for the central atom. X stands for the number of bonding regions or bonded atoms. So if we were to look at this again, the number of bonding atoms or bonding regions around the carbon is 3. 1, 2, 3. And E stands for the number of lone pairs. And the number of lone pairs around the central atom is 0. So then we would look up on our table AX3. And that would tell us that it's trigonal planar. Done. If, on the other hand, we have, let me get another. All right, if we have something like, where's my eraser? There it is. If I have something like water, 1, 2, 1, 2. Now, how many bonding regions do I have around the water? Around the central oxygen?
2.
2. Yep, 1, 2. And how many lone pairs do I have around the water?
2.
2. 1, 2. So when I did my Axe body spray this time, I would say A, my central atom is oxygen. It has 2 bonding regions around it, and it has 2 lone pairs. So I go to my handy dandy table that I printed out, or I have up on a window, and I see that since there's 4 regions of electron density, 1, 2, 3, 4, there's 4 regions of electron density. That means it's tetrahedral. That the overall group that it's in is tetrahedral. But the shape of the molecule is not tetrahedral. The shape of the molecule is bent. Because when we look at the shape of the molecule, we don't consider the electrons. But the electrons influence the shape. Because if we just look at the water by itself without the electrons there, it looks like this, right? And you'd look at it and say, well, that's a bent molecule. The reason it's bent, though, is because of the 2 lone pairs. The 2 lone pairs are in the tetrahedral shape. So we have 1, 2, 3, 4 electron regions in a tetrahedral shape. So it has a tetrahedral geometry, but it has a bent shape. Because with the shape, we don't consider, we're not looking at the lone pairs. When we look at a molecule, we can't see the lone pairs. We can see the influence the lone pairs have on the shape, but we don't actually see the lone pairs themselves because electrons are too damn small to see. We can see the atoms, but we can't see the electrons. So we're going to get to that next week. So if you don't get it right now, it's not a problem. We'll get to it on Tuesday.
So what do we fill out for polar or non-polar for the recitation? Do we just skip it since we haven't learned about it yet?
Well, it won't be, the recitation won't be due until Thursday. So, because we did it, yeah, I can make it due, I can push it ahead a couple days since we won't have a chance to get to it till Tuesday. I'll push it till next Thursday. But as far as polar goes, basically what you're looking at, the general rule, if it's symmetrical, if the molecule is completely symmetrical, it is non-polar. If it's asymmetrical in some way, it's generally going to be polar. You need to have polar bonds to make a polar molecule, but to make a non-polar molecule, you need to have symmetry. So for instance, carbon dioxide is non-polar, even though it has 2 polar bonds. So there's one dipole, there's the other dipole, but they're equal and opposite. They point in equal and opposite directions, so they cancel each other out. So, and carbon dioxide is a symmetrical molecule. It's linear. It's, you cut it in half. It's the same. It's a mirror image any way you cut it. And so it's a non-polar molecule, even though it has polar bonds. So basically, you're looking for symmetry. Are you doing the lab this afternoon, or you're in Professor Bates's group?
We did the lab on Tuesday.
What did you do on Tuesday?
We did stoichiometry of a precipitation reaction.
Okay. Yeah. So I'll push you guys ahead till. Actually, I'll do it till. I'll give you an extra week. How about that? Because this is something the other 2 groups sort of had a head start on. So I will change the due date for AD, push it ahead a week, all right?
Okay, thank you.
No problem. Because yeah, it's an important concept. It's going to keep coming up over and over and over. All right. Yeah, thanks for pointing that out. All right. Any other questions? We only got a couple of folks left. Anybody else hanging on with a question? All right. I will see you. Man, just like every day is the same. I will see you on Tuesday if I don't see you this afternoon. All right. Have a good morning. I'll talk to you soon.